Hello again. This is Math 1120 coming to you from the College of DuPage, and this is the conclusion of the lecture entitled Counting Techniques and Probability. As always, please be an active learner as you watch this video. Last time we left off with this slide and we had just defined what a permutation was, and remember it was an ordered arrangement. That was important, which our objects are chosen from distinct, different objects, such that repetition is not allowed, and that was NPR in this notation. And the formula for NPR was given down here. NPR is equal to n factorial divided by n minus r whole factorial. Now let's continue by calculating a couple of these using the definition that we just had. So this is 7p5. So here's the formula again. And so this is going to be 7 factorial over 7 minus 5 whole factorial. You always do the parentheses first. So 7 minus 5 is 2, so it's 7 factorial over 2 factorial. Now notice when I write 7 factorial, I can go down to 2 and just call that 2 factorial, but then it's 2 factorial over 2 factorial. So those things will cancel one with another, and I have these numbers I'm multiplying together, and I get 2520 for my answer. Similarly, 5p5 is going to be here, so that is 5 factorial over 5 minus 5 whole factorial. Now remember that 0 factorial was defined to be 1. And so this is just 5 factorial. We multiply those together and we get 120. We'll also talk about ways to use technology to do these calculations in the VCM. But let's apply this now to betting on a trifecta. And a trifecta means that you are specifying in your bet at the racetrack is which horse do you think will finish first, second, and third. And so the question here is, how many different ways can horses in a 10-horse race finish first, second, and third? Well, the 10 horses are distinct. Once a horse crosses the finish line, the horse cannot cross the finish line again, and so their order is distinct. And in a race, finishing order is important. You get more money if you win the race than finish second. So we have a permutation of 10 objects taken 3 at a time. And so 10p3 is 10 factorial over 10 minus 3 whole factorial. You subtract this first, that's 7 factorial. And you have 10 factorial over 7 factorial, which is this. And notice that the 7 factorials will cancel out. And so there are 720 ways that you can make this bet. So your chances of winning, if you didn't know anything about horse racing, you just randomly picking the horses, will be 1 out of 720. Now we're going to move on and talk about a different counting mechanism called combinations. Now recall that in a permutation, order was important. So ABC is different than BCA. Those are different arrangements of those letters, and you count them twice. But sometimes order is unimportant, and so there's not a difference between ABC and BCA. You might say, oh, were you selected to play on a team or not? It didn't matter if you were the first player or the last player selected, you made it onto the team. And in poker, that's another example, the order in which the cards are received really doesn't matter. The combination of the cards is what counts, and combination in here is a loaded word because it has a mathematical meaning. So here's the definition. A combination is a collection without regard to order, and that's very important. Is a combination is without regard to order, in which our objects are chosen from n distinct objects. The objects are still distinct, and r is less than or equal to n, and you can't repeat the objects. So you see the thing that you're relaxing here is that order doesn't matter, and we use a symbol NCR to represent the number of combinations of n distinct objects taken r at a time. I also often use, whenever I lecture on this, I call this n choose r because this represents the number of ways you can choose r objects from n. All right, let's do an example. This is listing combinations. So suppose that Roger, Ken, Tom, and Jay are going to play golf, and they will randomly select teams of 2 players each. List all possible team combinations. And so what we're really doing is there were 4 players, and we're selecting 4, choose 2. How many different ways can that be done? And again, it just matters who's playing together, not in which order that they were assigned. And so we list all the possible teams, and order is unimportant. So Ken Roger is the same thing as Roger Ken. And so here's the list of all the players. We have this, 2, 3, 4, 5, 6. And so 4 choose 2 is 6. So there are 6 ways of forming teams of 2 from a group of 4 players. Now we need a formula for this, and that's where we're going next. Okay, so this is the formula for N, choose R. And remember, this is the number of arrangements, different arrangements of R objects chosen from N objects, but the objects are distinct. Repetition is not allowed, and order is not important. So N choose R, or NCR, is N factorial over N minus R whole factorial. That's the permutations, but now you see we have to divide out the number of ways where the order was different, and that's going to be R factorial. And so if we're using this to solve the golfing problem, remember we calculated 4 choose 2, that is 4 factorial over 2 factorial times 4 minus 2 whole factorial. First thing you do is you do the things in the parentheses. 4 minus 2 is 2. So it's 4 factorial over 2 factorial, 2 factorial. So that is 4 times 3 times 2 times 1, that's 2 factorial. And this is 2 times 1, that's 2 factorial. The 2 factorials cancel. And so what you end up with is 12, 4 times 3 over 2 times 1. So it's 12 over 2, or 6, just like we had before. Again, let's do some calculations. So 4 choose 1, 6 choose 4, and 6 choose 2. Okay, so 4 choose 1 is 4 factorial over 1 factorial times 4 minus 1 factorial. First thing you do is the parentheses, that's 3 factorial. So that's 4 factorial over 1 factorial times 3 factorial. So that is 4 times 3 factorial, 1 times 3 factorial. The 3 factorials cancel, and that is 4. And that makes sense because you say, how many ways can I choose one thing from a set of 4? Well, you choose each one, so that makes sense. Here we go, 6 choose 4. That's 6 factorial over 4 factorial times 6 minus 4 whole factorial. You do what's in the parentheses first, so that is 6 factorial over 4 factorial times 2 factorial. So 6 factorial is 6 times 5, that's 4 times 3 times 1, that's 4 factorial. And then this is 4 factorial and 2 times 1. The 4 factorials can cancel, and I get 30 over 2, or 15. Similarly, 6 choose 2 is 6 factorial over 2 factorial, that is 6 minus 2 whole factorial. You do this first, so this is 6 factorial over 2 factorial times 4 factorial. Now, if you notice, this is the same number, so we're also going to get 15 for this. And so notice that picking how many ways can you pick 4 is the same number of ways you can pick 2 not to be in the set. Okay, so simple random samples then. The question here is, how many different simple random samples of size 4 can be obtained from a population whose size is 20? Well, the 20 individuals in the population are distinct. In addition, the order in which they're selected really doesn't matter, just matters if they're in the sample or not. So we're going to use 20 choose 4. It's 20 factorial over 4 factorial. This is 20 minus 4 whole factorial. You do the 20 minus 4 first, so that's going to be 16 factorial. So it's 20 factorial over 4 factorial times 16 factorial. This is 20 factorial, and I just leave the 16 factorial here. And then I have 4 factorial times 16 factorial. Notice that the 16 factorial cancels out. And if I do the multiplies, I get this, and that is 48. 45. So there are 4,845 different simple random samples of size 4 from a population whose size is 20. It's kind of amazing to me that the number is that big. Now, sometimes the elements are non-distinct. And you see, we're going to talk about permutations, but now these are non-distinct elements. That means you can't tell the difference from one to the other. Some of the objects are not distinguishable. And a good example of this is a DNA sequence. You see, a DNA sequence consists of a series of letters representing a DNA strand that spell out a genetic code. There are 4 possible letters, A, C, G, and T, representing a specific base in the DNA strand. And here's the names of those bases, and that's a biology thing that you have studied. So how many indistinguishable sequences can be found using 2 A's, 2 C's, 3 G's, and 1 T? Now you see, you can't tell the difference between either one of these A's, between either one of these C's, between any of the 3 G's, and there's only 1 T, so you can't tell the difference there. So what happens is then we got 2 and 2 is 4, 3 is 7, and 1 is 8. So you have 8 slots to put in. So the first thing, and we can think about this goes all the way back to the beginning, is we can choose the position to put the 2 A's. And then we can choose the position for the 2 C's. Then we can choose the position for the 3 G's, and there's only one position left for this. So you see, when we start out with the A's, there's 8 places that we can choose to put that. So it's 8, choose 2. But then we multiply our next test. There are 2 places gone, so there is the places to put the C's are 6 remaining places, choose 2, times 4. Now after we've chosen those, there's 4 places left to put the 3 G's, times 1, choose 1. And if we multiply all those things together, you do want to follow this calculation, you get this. Now you might notice that you have kind of an interesting pattern that happens here, but there's 1680 possible distinguishable sequences that can be formed, although some of them you can't distinguish from. This gives rise to a formula. And here's the formula. This is permutations with non-distinct items. The number of permutations of n objects, of which n1 are of one kind, n2 are of a second kind, ... and nk are of a kth time, is given by n factorial over n1 factorial times n2 factorial ... times nk factorial. But you have to insist that if you take all of these n sub 1s, they add up to the n that we have in the formula. Again, this is another important formula. Let's apply this to make it real. How many different vertical arrangements are there of 10 flags if 5 are white, 3 are blue, and 2 are red? Now, if you notice here, 5, 3, and 2 all add up to 10, so all of them are represented. So, and this is a permutation because the order matters. So using the formula then, you have 10 factorial over 5 factorial times 3 factorial times 2 factorial, and that ends up being 2520 different vertical arrangements. Now, one of the challenges in solving counting problems is selecting the appropriate formula. And here's a summary, okay? So we can have combinations where order does not matter. We can have permutations with replacement, permutations without replacement, and also non-distinct items. So there's a bunch of things to keep straight here, and this is very worthwhile studying this as a summary. But we can also use these to solve probability problems. So let's talk about one of these. In the Illinois lottery, an urn containing balls numbered 1 through 52. From this urn, 6 balls are randomly selected without replacement. You don't put them in. So for a dollar bet, a player chooses 2 sets of 6 numbers. To win, all 6 numbers must match those chosen from the urn. The order in which the balls are picked does not matter. That's the way the lottery works. What's the probability of winning the lottery? Well, you're just picking this, and so you're saying how many different ways could 6 numbers be picked from 52. So it's 52, choose 6. Here's a formula, 52 factorial over 6 factorial times 52 minus 6 whole factorial. The first thing you do is that's 46 factorial, and that will cancel out with the numerator, and so you can do the calculation. You get there is a little bit more than 20 million possibilities. Now each ticket has 2 chances of winning, and so if E is the event of having a winning ticket, then it's 2 out of that. And if you do this arithmetic, and it's around 1 out of 10 million possibilities of winning the Illinois lottery by buying one quick pick ticket. Another applied example, suppose a shipment of 120 fasteners arrives, and it contains 4 defective fasteners, and this was sent to a manufacturing plant. The plant's quality control manager selects and inspects only 5 of these fasteners. What's the probability that exactly 1 of the inspected fasteners is defective? Okay, exactly 1. That means 1 and no more than 1. So the probability of 1 defective fastener is going to be the number of ways that you can pick that defective fastener. And you see there were 4 defective fasteners. We're picking 1 of them, so that's 4. Choose 1. But then, after we've picked exactly the 1 defective fastener, we have to pick all the others and not pick any more of the defective fasteners. So there are 116 from which we choose the remaining 4. So we multiply these two numbers together by our multiplication principle that we discussed in the last lecture, and that tells us that there are 28,640,980 ways that can happen when you multiply those two numbers together. But then you have to say, but how many total ways could I have picked 5? Well, there were 120, and the order in which you picked them doesn't matter, so it's 120, choose 5. Is this number, so you get this as the probability of selecting exactly 1 defective fastener. We are going to have, and I might as well mention, an LSA 8. Their LSA 8 will be posted in your syllabus tab, and also there'll be a slot to do it, and it'll be mentioned in your announcements. But here's LSA 8. How many randomly selected people must you gather into a room until the probability of matching birthdays exceeds 50%? Now assume that every birthday is equally likely. That's actually not true, but make that assumption, and that there are 365 different birthdays for your calculation. Show and explain your work for this answer. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and of each other. May God bless you all.